Hey, this is Steven from LegitTechTutorials, and welcome back to the Shredder product design tutorial series. So we are back designing pieces of the Shredder, and one second. Let me go ahead. Okay. So we are back looking at the designs of the Shredder. So we are pushing along here, getting close to. Today is the 31st, the 31st of October, and then tomorrow is November 1st. Well, this is 12 o'clock in the morning, so, midnight, so it's 10:31, barely, by 17 minutes. So we are still trying to be on time for launch and at November 17th, the Kickstarter. So we're going to do a few more things, and then this guy's going to be ready to go. So I took the class on Saturday. I took the water jet class on the machine that I'm going to use as a manufacturer's guide at Tech Shop, and they had an issue with it, and basically the water jet water pump was not hitting 60,000 psi. It was only hitting 20,000 psi, so they're thinking it's an air leak. So hopefully they fix that, otherwise it could be an expensive fix. And as you know, Tech Shop's on the rocks, so they might not fix it. I don't know, we'll have to see. There's going to be another one in a week or 2 weeks in their class, and I'll sit in on that class and see what's going on. But that will put us really close. Hopefully by next week we could figure this out and have this done. I'm going to probably be doing a video on this every week, but I'm not releasing this as I'm doing them. I'm still doing my other series with my other product design series, the automatic spooler and dimensional control module. So instead of, you guys could follow along as far as the dates. I tell you what the current date is on the that I'm working on it, so you could follow between now and November 7th of filming the video, whenever you do see this. So we are pushing forward to hit that deadline. We have to manufacture. We have to do a prototype and then shoot the video, and then so it doesn't necessarily have to work perfectly. It just has to be able to shred plastic for the video, and then we'll have a month while the video is going on while the Kickstarter is going on till December 17th, and then 15 days before we get the money to manufacture it. And in between that month and the 15 days, we could redesign it and make it better. So we have some time. So we're just kind of roughing it out. So that we could produce a prototype and then shoot the video and then go into the Kickstarter and then spend the 30 days plus 15 days, 45 days redesigning it and getting ready to launch, and also I'll spend those 45 days getting the multi-shooter project finished, plus the other 17 days. Alright, so what I've been doing recently on this guy, so I've started to do some simulations here. So let me go ahead and show you guys how I do this. Let's go ahead and just start, just delete everything. So I've been messing around with this just so I could show you guys how I do all this stuff. So what I'm going to do is go into model view. Alright, so basically how you do a study is you click here, and then you have the four different ones: static stress, model frequencies, and this is basically resonance frequencies, thermal, which is, heat, and then thermal stress, so thermal expansion and stuff like that. Yeah, thermal expansion. And I think this is actually thermal stress. I don't know if it's expansion. Oh, it is. Okay, so it is thermal expansion. Thermal expansion and thermal expansion, thermal stress. So this is a combination of this one and this one. And then there's not really any other things. There's no aerodynamics or friction or anything like that. It's just all mechanics. Alrighty, so what you do on this guy is we are going to create a quick study to look at the stress that we put on this guy here. And we're going to do that by, you click here. I'm already in static stress right now. So of course this is statics, meaning that this body cannot rotate. So we want to go into constraints, and we're going to do a fixed constraint. We don't want a pinned constraint. We don't want a frictionless. This is a roller. So these are the three main types. There's fixed, pinned, frictionless. So fixed has 3 forces on it: torques, X, and then Y. Usually we limit to X and Y. In this case, it could be Z. So theoretically, you have moment, X, Y, Z. And then pinned, you're only supposed to have pinned is just moment and then X and Y. It's one less than fixed. And then frictionless is only above the friction. Basically means roller. It's up and down Y of the plane that the roller's on, and a moment. So this one will have 2. So I think this one has no moment. Yeah, something like that. All right. So but we want fixed. So what we're gonna do is we're gonna set this guy to fixed. And why we're doing that is that we're doing this because that's where the bar goes through. And so we are going to we're going to say that that's held still, and then what's going to happen is that we're going to put a pressure or a load. And you have some different loads. We have load, pressure, and pressure is a distributed load normal to every location on the face. So this is force over area, and moment is a rotation or torques, and then we have remote. I guess that's like off the model or something, I don't know. Anyways, so we're going to do a force, and then where I'm going to put the force is I'm going to put the force right on the corner here. Oh. And then I'm going to do an angle. Oh, what the hell? Cat's kind of freaking out again. Sorry about that. So loads, constrain. Let me reconstrain everything again. Sorry about that. I can't remember what the pin was. Which loads the pin doesn't have. I thought it was moments, but that's not correct because I always take moments with respect to pins. I think it's like the same thing as a fixed. It's just like minus one of the things. I can't remember. Why is it? Oh, because I have all the things still selected. That's why. There we go. Alright, so then we do angle, and we're going to tilt this guy. And this is our cutting face. So this is where, so we're doing shear. Basically, that's what we're doing. So we're looking at shear. So the idea is that here would be one, and then the other one would be over here or down here. It's the same thing. I mean, it's symmetrical, so most likely the other piece would be down here at that face. So there will be 2 of these blades meshing at this one point, and that's where it's going to cut. I guess you could theoretically say that it's a pressure load, where it's, the force over this area, which I don't know if they have a distributed load. I think the only type is the pressure. It's that general force there. And we're in US units, so we're going to look at PSI, and then here we're just going to take a look at pounds force. So shearing of a to cut a piece of material, usually you look at the tensile strength, and you take a 0.60, so 60% of that is usually a good estimate of what the shear, is usually what the shear is. That's just kind of a good idea. So let me see. Ultimate tensile strength of ABS is 40 and PET is 55. So that means ultimate tensile strength means that that's when it breaks. So we're looking at and this is force per area. And in shear, we're talking about the cross-section area. Shear is parallel to the cross-section of area. So it depends on how thick the ABS sheet is, how thick the piece of ABS you're cutting. And that's with and like I said, shear is parallel to the cross-section. So, for example, if I was cutting this guy with if I had a blade here and the blade on the bottom, or because what's going to happen is when this meshes, there's going to be no gap in between this. So the only thing that we're going to keep into effect is basically what fits in between these two blades. So on this guy, this would be our area right here. Basically what fits in this piece here. So let's take a look at that. Distance 0.62. So let's just do a square. Or you could do two triangles. So let's just do 0.62. Let's just do 0.62 by 0.62. And that was in inches. 0.62 multiplied by 0.62 multiplied with 0.62. It's 0.3844. 0.3844. Let me save that on my other screen. And we're 0.602 inches. And then we're going to turn that guy into PSI. Uh-oh, where'd my force go? Oh, I'm looking at the wrong one. Put the load back. Okay. And so basically force over area, so what we're going to do is we have 0.388 and then you need to do megapascals to PSI, and we're talking 40, so that's 5,801. And then, so that's force per area, so we're going to multiply that by area and get the force. So 500, and that was 0.602 multiplied by 0.602. So this is, of course, this is the maximum. Actually, this is the... The maximum would be if it was minimum area. That's interesting. 0.8. So that's 2,102 multiplied by 0.60. So that's 1,200 and something. This is gonna be good. This is gonna rip this steel apart. That's pretty much what's gonna happen here. Alright, so then we're gonna solve. Of course, we're just kind of BSing around, seeing what's going on here. Okay. Alright, so this is what we got. So what we're looking at here is safety factor. So what safety factor is if we look over here in the material, you'll notice that we're using 4040. I changed it to 4142 steel. Tomorrow I'm gonna call up Sims. This is where I get all my steel. So I'll call up my buddy down there and see what type of steel he normally sells. And we're looking at yield strength. So if you're not familiar with yield strength, what it means is that is the point at which the steel starts to fail. And when I mean fail, it means that it's starting to deform where it won't bounce back. So it's permanent deformation, otherwise known as plastic deformation, which means that it won't snap back to its original shape. If it's not at that point, it means it'll snap back to its original state. And then what you see here, here's the yield strength, which is 199,000 psi. And ultimate tensile strength you see is a little bit higher, another 5,000 psi. And you see Young's modulus. Young's modulus is what influences the. Oh, got some hair under my mouse. The Young's modulus is what influences the yield strength. Young's modulus is basically the slope of the stress versus strain graph. And so what the stress versus strain graph looks like let me see if I pull it up. There's 4130. Here's 4130. Let's just view this. Okay, so here is 4130. 4130 steel. So you see here that there's like a linear portion and then there's a rounded portion. And basically the rounded portion here is where you have the stretch and the fail. So this is the plastic deformation, and then this is the elastic. So let's say if you put on a force, or in this case it's a pressure. MPa is pressure. So stress is force over area, which is the same. It's internal stress. So you have force, which is newtons or pound force, and then you have pressure, which is force over area. So stress is internal pressure, force over area, internal force over area. So this is your PSI or megapascals, and true strain is delta L. So your deformation of the steel, because no matter what pressure you put on something, it will deform. Now, if you put very little pressure, it won't deform at all. But if you put a lot of pressure, I mean, it won't not deform at all. It will be so minute that it could be just counted as negligible. But here is a so the more pressure you put on, the more it deforms. So the farther up you have over here, this strain is delta L over the original length. So it's like it's a unitless number, and yeah. So if you go here, as you go over here, it's starting to stretch. So here at the peak of any one of these, you have the ultimate tensile strength, and that's when the maximum amount of pressure that something will take, and then shortly after that it fails. So the end of these lines is basically where the piece fails. So this is an idea. The Young's modulus is this, and the yield stress is I was at 0.02 offset, 0.0. It was a 2%. Was it 2% or 0.2%? 0.2 or 2% offset is usually the standard. So you go over here and then you go up with the same slope as the Young's modulus, so parallel to this line, and then whatever point you hit, that is your yield strength. and that yield strength is the point that we consider that plastic deformation happens. So that's where this yield strength comes from. I think it's, I can't remember, 2% or 0.2%. It might have been 0.2% offset. Is where you go over 0.002 and then you go up, and then that's your yield strength with the same slope as the Young's modulus. So that's the number we have right there, 200,000. So at that point, we're considering that elastic deformation is going to happen, and that's what we don't want. We're considering that the fail point. So you could look up ultimate tensile strength, but that's basically right as the part's going to fail. It's going to snap off. Here is right as the piece is going to start to bend and not come back to its original shape. So let's go ahead and look at that again. So we're looking at safety factor. Safety factor is the applied, it is the yield strength. So whichever one we picked, yield strength or ultimate tensile strength, it's that over the given pressure, right? So over the applied pressure. So you saw that our yield strength for this guy was 200,000 psi. So if we go over here and we go into our stress, you see that this is 170. So if we go into calc, we put 200,000, right? 200,000 divided by 170, 137 equals 1.17. You go 1.17. So that's where you see the number comes from. So it's your maximum yield strength, or your ultimate tensile strength, your yield strength or your ultimate tensile strength over your applied stress, and that will give you your number. So basically, what this means is how safe are you from this part failing. So if you're at 1, that means that your yield strength and your applied stress are the same, and it's pretty much going to fail. So you want to stay as far away from 1 as possible, like this guy right here. 15 is 1.175. So that means that this guy is about to fail at that, oops, what the hell? Is about to fail at that point. So what we might need to do is look at hardening these guys. These guys are definitely going to have to be probably hardened. I'll have to figure that out on how to harden these guys. But you see here that it's going to have, if my calculations are correct, they're going to have to work pretty hard to get the PLA to cut. Alright, so that's one, and then I was working on another one. This is for the deformation. Also, another thing, you'll notice that on this guy, if we go here and we go deform scale adjusted, we'll actually see what it's trying to do. So this is the because as I said, no matter how much pressure you put on there, it's going to deform, whether it's minuscule in the point where it could just be forgotten, or what's the word I was looking for? Negligible. So you just don't even count it, to the point where it's very noticeable. So this option here for the adjusted is to give us the view, the exaggerated view, to give us an idea of what would happen under high loads. So we'd see that here, what it's trying to do is it's twisting, it's doing a little bit of torsion on this piece here, where it's twisting this piece back. You kind of see the shadow of where it used to be. So you see from here to here, not very much, and from here to here, quite a bit. And then you can see that goes with the stress, and you can see the color code. You can see the color code of this guy, which is, if I go down on here, you can see the different. So this is where the stress is the most, and you see down here it wants to try to rip that guy down there. But the most stress is down in that leading edge, this leading edge here. So if we want to check that out, we can go into displacement mode, and we see the total displacement. The maximum displacement is at this far tip, which is 0.004. And we see that that's which is, what is it? That's 4 thousandths. So it's only 4.4 thousandth of an inch, which is very small. So that's why if you go to actual, it's like very, very small. You see it goes from there to there. Very, very small. But the main, and then you see here it's like nothing. But you see that it has a point where, and we see that the minimum is actually right here. So maybe we'll thicken this guy just to keep this guy from curling. So maybe we'll go from here to here. We'll change our design so that this guy doesn't want to peel back so hard. And we'll manipulate this to try to get this to be the highest number possible. Alright, so here are some surface probes so we could look at what the different things are. So here we're at 3.5, 4, 5, 6, 7. Here we're very low. And then you notice that nothing really happens over here. Alright, so that's one test that we're going to use to develop some of our stuff. I need to actually change this a little bit. So this is kind of interesting. I'm going to definitely be using this during the 45 days to get this to work, but I was just doing that to see on a ballpark how well it was going to work out. So from that, we're definitely going to have to why? Let's see what that does. I'm trying to get this to be a better represented, because it's taking too many small slices out of the thing. You see now it's taking a lot longer to do anything because I boosted up the size a little bit. Okay, that's all. So now what we're doing is we're doing a torsion test. And basically what we're doing is I set these guys to constrain. So now these tips are not moving, and the only thing that is moving, the only thing that is twisting is there's a moment on this shaft where these guys come into contact. Okay, so let's make this 3. What was this last one? 40. So let's make this 3, 10, 20. 3, 10. And keep that 40. So I'm trying to get this to be a better shape. Huh, interesting. Here it says high density polyethylene is only got 15 megapascals ultimate tensile strength, and PET has 55. So here we can see we got slightly better of this guy. But yeah, oh, this guy changed. Why did I do that? Where was my constraints? Okay, so what I want to do is I want to look at the twist of this guy and see if it's gonna how much it's gonna shear. So for example, let's do what I'm talking about here is I put a moment at the top of this guy. Right now it's being super dumb. Let me leave and come back. There it goes. Okay, so there are my constraints. So basically it's not going to let this guy turn. I mean, I don't really need a constraint there, but what happens is this thing stays there and this guy tries to rotate. So what I'm doing is I'm putting a load, and let's just delete that. I'm putting a load, which is a moment, this guy, and then this is a pound force. So right now, we could see how much torque we could put on this motor, what type of motor we need to cut and to take this guy to fail, pretty much. So let's do like 1,000 pound force, and then solve. And then this should be quicker. But what I'm looking at is I'm looking at what type of degree of twist we're going to get. So in torsion, we have the twist of the mesh, and also, you know, it will have a lot of internal stresses as well with torsion. So I'm trying to see what type of solution we're going to get here. Oh, so it has a lot of refinement here, which is not really needed. Interesting. Does it have any other thing up there? So minimum is 1.259. And the max is 15 here. So can we see displacement? So all of the force is in here. Let's just get rid of the blue. So here's some force here. Interesting. So let me go into so let's see what like the adjusted. Yep, so there's the torsion we're looking for. So there's the twist. And then let's bump it up higher. Whoa. What the hell? Yeah, there we start to see some weird torsion. Okay, I don't know if this is really the test I'm looking for. What I want to try now is come from the bottom. And then I need to make sure this is rotating the right way. Rotating the opposite way. Rotating this way, yes. Okay, let's solve that really quick again. So this is going to give me an idea that definitely for the Kickstarter units, I'm going to have to harden the steel. Not necessarily case harden, but harden them in a furnace. So I'm going to have to find a furnace to heat treat and then quench these steels to... let me go to actual. that's interesting. It has a lot of stress in here. So here's the stress, and here minimum just 3 psi, which is pretty low. Alright, so let me look at probes. Surface probes. So here we're looking at 12, 12, 12, 11, 11, 12. Okay, so here it's got a little bit of twist and displacement. Oh, there it goes. What? Why is it doing that? So it is deforming. It is starting to twist. But it's mainly up here in this section. It's interesting. But then it just dissipates a lot of the force in here. But yeah, the main issue is that if you take this piece off, it starts to rotate. It starts to want to turn. Alright, so I mean that's pretty much what I wanted to go over. So this gives me a good idea of the type of stress that this material is going to go through, and it's definitely going to have to be a hardened steel, heat treated and then quenched, tempered steel in order to cut these things. But then if it's tempered steel, it means that generally I'm going to lose ductility. And these things, when they break, they're gonna fail. Brittle. They're gonna be brittle. So they're gonna have brittle fractures instead of ductile fractures. So I'm gonna definitely have to do a lot more of this testing later on. But we're going to push forward with pushing forward these pieces. And then if on the prototype I need to heat treat these guys, we will do so. But again, like I said, the design here is not as important right now as it will be when I get ready for when I get close to the Kickstarter. As the Kickstarter is going through, I'm going to have to go through and edit these guys and keep going back to from here to the study, and then from that entire time get these dials to be, get these cutter wheels to be the strongest that I could get them. Alright, so that'll pretty much be it for this video. I'd like to thank you guys for watching. If you like this video, please subscribe for more reviews like it in this series and other series as well. I'll catch you guys in the next video. Thanks for watching. Take it easy. Peace.